in this case, instead of doing all possible r's from 0 to capital R, the distance is only given as a small r. So in fact, in this case, it does not have any dependency on r, on radial direction. All the control rods is inserted uh, from r distance from the center of the vector. So instead of doing that integration, so this will be simply, instead of doing that, now let me just rewrite this. So in fact, it does not have any dependency on R and any dependency on the omega azimuthal direction. So to calculate dv is actually calculated as, we don't have any dependency here, so it must be AC. So AC is the cross-sectional area of the control rod. So if we go back, the control sectional area of the control rod here, and X would be the distance. X is the depth that control rod is inserted. So if we simply want to calculate the volume of the control rod that is inserted into the reactor, that would be the cross-sectional area A multiplied with X. So just like that. So because the integration should be performed only for the volume taken by the control rod, so dV becomes AC, so cross-sectional area of the control rod multiplied with, so very small increase in Z, and all other parts will become constant. So it should be originally written like this, and G should be from h over 2 minus x to h over 2. And so now we are on the right track. So c square is constant, and with respect to z, the Bessel function is also a constant. So we take them out, and AC would be also a constant with respect to z, because the cross-sectional area does not change as z changes. So this is what we should do. They are irrelevant to the R or the cross-sectional area. It is only dependent on the depths that the control rod is inserted. So in this case, instead of actually calculating this in a similar manner, we will be able to calculate RH. So let me first write this. So RH will indicate that the reactivity when that control rod, exactly the same control rod. So in our textbook, this control rod is inserted fully to the bottom of the reactor. So this reactivity will be, the reactivity for this would be, so integration should be performed from minus h over 2 to h over 2. So the when we divide the first with the second, over r rho rh, then what we are going to get would be this ratio. This would be the equation for when the depth of the insertion is x, and this would be the equation when the depth equals the depth of the insertion is h. So when only x is inserted, and this would be when the control load is fully inserted. And all these constants will disappear. All these constants will disappear. And if you do calculate that, so it will not be very difficult for you to do this integration. And what you are going to get is the equation that you can see in equation 7.86. So x over h tilt, x over h tilt minus 1 over 2 pi and sine 2 pi x divided by h tilt, the extrapolated distance, extrapolated height of the reactor. So of course, if we move the rho RH, the reactivity change when the control load is fully inserted, then we are going to get the equation that is shown in 7.86. And also, it will not be very difficult for you to draw the figure 7.8. So, let's see, 7.8. So figure 7.8 is the direct application of equation 7.86. So, yes. Of course, this will not be very difficult. So this would be partially inserted control load case. Let's define t as from 0 to 1. And what we want to calculate is, in fact, x minus 1 over 2 pi. I think this pi will give us the pi minus, I'm sorry, not x, it should be t. So t minus 1 over 2 pi multiplied with sine of 2 pi t. 2 pi t. Then if we plot t over x, t and y, of course we can get this equation, this figure. So in x-axis we have the ratio of the ratio of the depth of control load insertion to the full to the height of the control load at the height of the reactor. In other words, the amount of distance that control, the amount of depth that control load is able to insert it. And of course, from when as the insertion, as the control load inserted more and more, then the ratio to the reactivity compared to the fully inserted case may increase, and this would be the case when control load is fully inserted. And next case would be, and if we change its radial direction, then the Rx, so R0x would be the case when we insert the control load at the center of the reactor in the axial direction. So compared to that, the change would be the square of a Bessel function. So of course this would come from here. So when r equals 0, this Bessel function would become 1. So the change, the ratio will be given as the J0 is given to this amount of Bessel function. Next, we would like to see when the control, instead of a single control load, we would like to see the case when control load bank is inserted. So this figure 7.9 gives us this case of control load bank insertion. And one example, one assumption that we make to solve this problem is that we are going to assume that control loads are kind of uniformly distributed over this cross-sectional area of the reactor. So that means in the radial direction we do not have any dependence on in terms of what is that? In terms of the effect of control load. So we do not have any effect on the radial direction. So that means it is like we are inserting a uniformly distributed control loads. The control loads that is uniformly distributed over the cross-sectional area of the reactor. So of course, in reality, control load will be placed in many different places. But that would be the assumption that we make to simplify the analysis. So how can we how can he solve this equation? So we are going to utilize the equation that we used previously. So after inserting, so so we are going to assume that, of course, the difference is that after inserting the reactor, after inserting the control rods, so I'm kind of hesitating at this point too, because if my explanation is not clear enough, you may be somewhat confused with this K. So let's talk about the control rod bank insertion case. So before inserting control rod bank, and this would be when the case, that is when the reactor is in the critical state. So in the critical reactor, in fact, this would be the equation, the neutron balance equation that we learned in our previous semester. So the first term is the leakage term, the second one is fission neutron term, and the third one would be absorption term. So they may, so if they are well balanced, then we are going to get a steady state solution for phi. The steady state solution means that the reactor does not, the reactor the reactor flux, neutron flux will not change. In that case, we are going to have a steady state constant reactor power. So that is the case of a critical reactor. So after inserting the control load bank, so previously K was used to indicate the case that indicates the case before the case of the case before inserting the control rod. But in this case, this K is used for the case after inserting the control rod. So in that case, K will not be after inserting control rod, then K will not be 1. So in that case, in this case, if we do not provide 1 over K, this would not be 0. So however, if we properly insert 1 over K here, then now the right hand side becomes 0. So this would be the equation. This would be kind of diffusion equation when k is not k is not exactly equal to 1. So once again, so we are going to slightly manipulate the equation. So instead of sigma, instead of new sigma f, so once again, I think you have seen this operation many times. So this part, new sigma f over sigma a, now becomes k infinity. K infinity. And we have sigma a phi and sigma a phi. So I'm going to place a sigma k infinity in the numerator here. And now we have a sigma a phi minus sigma a phi. So that is going to be minus 1 sigma a phi equals 0. So of course we are going to divide each term with d and try to find the solution for this. And in case of one group solution, if we divide sigma a with d, we are going to have 1 over L squared. So, and when we utilize two groups, then instead of L squared, we get m squared. So that's what we actually studied in our that we studied the last semester in nuclear reactor theory course. So this part, so in one group we are going to have L squared. We are going to have L squared in when we get one group solution, and when we get two group solutions, then m squared equals L1 squared plus L2 squared. So we are going to start from this. So let me change this to like this. So for uniform cylindrical reactor with the height is the same with the diameter, and the diameter equals 2 times of its radius. So in this case, we do not have any dependency on its azimuthal direction. So neutron flux will only depend on the radial direction and axial direction. And by applying the separation of variables, we are psi for r direction and chi for g direction. So by applying the separation of variable technique, of course here we need the how Laplacian is given. So in fact Laplacian is given. So Laplacian is given. And when we do not have any dependence on the azimuthal direction, then Laplacian will be given as 1 over r 1 over r d dr, and r d dr, and phi. So the phi should be placed here, plus in g direction d squared g, d squared phi, and d g squared. And also phi would be like this. So well, it is already 4:16. So why don't we take a short break? And then I also would like to ask all of you to leave your name to check your attendance. So we are going to resume today's lecture at 4:30. Yes, let's start the second part of today's lecture. So, I wrote this equation. To remind you how we applied the separation of variables in case of a cylindrical coordinate system. So when we divide each term with phi, in other words, the psi multiplied with chi, then in that case, of course, first what we can see is that this is derivative with respect to r. So for that reason, chi can be taken out here. So what we are going to see is that this is only a function of psi. So in this case, of course, psi, which is only dependent on r, will not be affected by derivative with respect to z. So this can be taken out. So in terms of z, this psi function is simply a constant. So the derivative with respect to z is only performed on chi. So if we divide each term with psi and chi, so in this case chi will be deleted. So what will be remaining is only 1 over psi. 1 over psi will remain here. Also, if we divide this with psi and chi, then psi will be deleted, will disappear, and 1 over chi will remain. So equation is now changed to this. And I hope you also remember how we solve this equation. So the first term is only dependent on r, and the second term is only dependent on z, and the last term is simply constant. So if the sum of these three terms to be 0, then that means it becomes 0 for any value of r and any value of z, then the first term should become a constant, like minus br squared. Minus br squared. So if we solve this equation, then we are going to get a Bessel function. So that means, because this is a constant minus br squared, what will be remaining would be so think about this, minus br squared. The first one is minus br squared plus 1 over chi, and so with this equation, if we multiply chi to all the terms, so I'm going to move minus br squared to here, and if we multiply each term with chi z, then we are going to get this equation for chi. And this would be applicable not only to the area that control rod is occupied, not only the volume that is occupied by the control rod, but also the volume occupied by the nuclear fuel and moderator. So the same equation, and in fact what we just calculated, what we just got was equation 7.89. So this 7.89 not only applicable to this volume that is occupied by control rod, but also the volume occupied by the core. And to solve this equation, RODED. So for the volume occupied by the control rods, so we call them as the roded volume. If we see our textbook, this shaded volume is the roded volume, and unshaded volume will be called as unroded volume. So for this shaded volume, the multiplication factor will be different because it is occupied by control rods. So we are going to assume that the K infinity, of the roded volume simply R, will be, there would be some slight difference. So simply K infinity will be the multiplication factor for unroded volume multiplied with n minus some amount of K infinity because of the insertion of control rod. So we denote this as delta, and this change is also proportional to the worth of the control bank. So we call this part is called as delta rho of control bank. Rho of bank. So in uncontrolled, in unroded volume, then the multiplication that this K infinity is going to be this is simply K infinity, and in unroded volume, then we can see some decrease in K infinity, and the amount of decrease is also proportional to this rho B, which indicate the worth of the control bank. So then we need to now divide the volume into two volumes. So we now have unloaded volume and loaded volume. So U for unloaded and R for loaded volume, respectively. So we have the same equation here. So of course, this chi is a function of z. Chi in function in the axial direction, and so this would be the equation for unloaded volume. So we are going to have a multiplication fact. The k infinity is simply k infinity is placed here, and of course this would be the chi for unloaded volume. For loaded volume, the equation would be slightly different. So, of course, first, for unloaded volume, in our textbook, for this unshaded volume, the volume that is not affected by this control load bank, and we are going to simply replace this with alpha squared. So we'd simply replace this part as alpha squared. Alpha squared. So that means alpha squared is defined as this parenthesis. So for unloaded volume, so the difference in the unloaded volume is that first for the loaded volume, we are going to use chi r and chi r, and instead of k infinity for loaded volume, we should use k infinity and multiplied with 1 minus load worth of the control bank. So if we divide this, then in fact it is the same. So this should be 0. And if we take out this low, the reactivity worth of the control bank, rho b, then of course this will be separated by k. So I'm sorry. Let's write it in this way. So minus, this is the first term, and already placed the minus here, and this would be, this is for the second term here. And I'm going to rearrange this to here by rearranging this. This is what we so after rearranging this, we know that this part is alpha squared, that is defined previously, alpha squared here, and the remaining part will be defined as beta squared. So these are the definitions given in our textbook. These are the definitions in 7.93 and 7.93 and 7.94 are the definitions of alpha squared and beta squared. So this will be rewritten as alpha squared. These are defined as alpha squared. This would be defined as beta squared. Beta squared. And this would be the definition of alpha squared and definition of beta squared. So from here, we are going to apply boundary conditions. So what would be in our textbook? What would be the boundary condition? So even though in the axial direction, different functions will determine the shape of the neutron flux, but in the boundary, when z equals 0, then neutron flux in the g direction should be 0. In other words, when z equals 0, so this is an unloaded area, unloaded volume. So when z equals 0, neutron flux should be 0. In the upper boundary, of course, at g equals h, the neutron flux, the loaded neutron flux in g direction should also be 0. So chi r at when g equals h tilt should be 0. So that means so in case of unloaded is 0, and the loaded one, and h tilt must be 0. So these two conditions should be satisfied at the boundaries, lower and upper boundaries of the reactor. And what about interface condition? Interface condition. So go back to our textbook. So in the interface, first, neutron flux should be continuous. So neutron flux in unloaded volume and neutron flux in a loaded volume at the interface should be same, so that the neutron flux can be continuous. And also, neutron current should be continuous. That means the first derivative in the unloaded volume and the first derivative in the loaded volume at the interface should be same. So so in fact, before so of course, before applying these boundary conditions, what we are able to see is that before boundary conditions, let's first talk about solutions. So what would be the solution for chi u? of course we should be able to compare their magnitude, but if we go back to this equation, this equation only tells us that this should be this should be constants. So if alpha is always bigger than 0, if alpha is always bigger than 0, then in the unloaded area, in the unloaded volume, the solution would be C multiplied with, in fact, sine and cosine. So if alpha is always bigger than 0, sine and cosine will satisfy that equation. And the boundary condition, if we apply the boundary condition here, so I'm sorry, instead of writing C1 sine and C2 cosine here, let's apply the boundary condition together. So with the consideration of the boundary condition, the solution would be let me show you the textbook once again. So that means it should be either sine or cosine, and when g equals 0, it becomes at g equals 0, the function, the neutron flux, should be 0. So between sine and cosine, the sine function satisfies that property. So in fact, this should be some constant multiplied with sine alpha z. So because we are currently solving this equation, so alpha z plus another constant and cosine alpha z, but cosine part, that the constant for the cosine should be 0. So that means only sine part will remain. So, and what about unloaded part? Loaded part. So here we see the equation for loaded part. So it depends on whether alpha is bigger than beta or beta is bigger than alpha. So so when alpha is bigger than beta, then once again we are going to have a sine or cosine function. And if we also think about the fact that at the boundary we should have the flux, we should have the 0 flux at the upper boundary. So basically it has some constant multiplied with sine of here, because we have alpha squared minus beta squared, it should be square root of alpha squared minus beta squared and z and the distance from the top minus g. So if it has the form or sign of some constant multiplied by h minus g would be the distance from the top, from the upper boundary. So in that case, at g equals h, it means that sine 0, the function. So only sine function will satisfy that property because cosine 0 will not be 0. Cosine 0, because cosine 0 is 1, so that cosine part will not satisfy that equation. So this is the case when alpha is bigger than beta. This is the case when alpha is bigger than beta. What about the case when alpha is smaller than beta? Then we should have a sine hyperbolic function. And I hope you remember what sine hyperbolic and cosine hyperbolic functions are. So, and the interface condition is that at the interface h tilde minus x is the depths that the control load banks are inserted. So if you see figure 7.9, so if you see this figure 7.9, x would be the depths that control load banks are inserted. And this is the point g equals x h tilde minus x would be the place of interface. And this would be the flux in the unloaded volume, and this would be the flux in loaded volume, and they should be same. This would be one condition to satisfy the continuity of neutron flux. And to satisfy the continuity of neutron current, then its derivative. In other words, its derivative with respect to z at the point of interface. At the interface point of interface should be when z equals h tilde minus hx. This should be same with the first derivative for unloaded flux. Of course, this comes from the fact that neutron current is given by the gradient d, the diffusion coefficient d multiplied by minus d gradient of neutron flux. So if d in the loaded and unloaded volumes are same, then we are going to get this equation. So what does that mean? So if we multiply the first condition, then in the unloaded, this should be same with, unfortunately, in loaded condition. So here, instead of h tilt, instead of if we insert h tilt minus x, then what we are going to get is simply x. So maybe we'd better insert this inside of the parentheses to avoid any confusion. One thing. So I'm sorry. If beta is bigger than alpha, if beta is bigger than alpha, then of course beta should be bigger. And of course beta should be bigger. So because always inside of this square root, we should have a positive value to get real number solution. And of course this is the case when beta is bigger than alpha. So this is one equation by applying this continuity of neutron flux condition. And of course, after differentiating xu and xr, if we differentiate this, then what we are going to get is differentiate, then we are going to get alpha should be multiplied, and then this function becomes cosine. And at the point when g equals h tilt minus x, so this is one condition. For loaded volume, then the right hand side would be if we differentiate this with respect to z, then of course we have a minus g, so minus and minus and square root of alpha squared minus beta squared, g prime, and instead of sine it should be cosine function when we differentiate and insert h tilt minus x, the right hand side. If we differentiate the chi r and then insert h tilt minus x, so similarly we are going to have a cosine hyperbolic function. So at this point, what we would like to do is to eliminate C and C prime. So if we eliminate, if we divide one with the other, then in the left hand side, C will disappear. In the right hand side, C prime will disappear. But it depends only on we are going to divide which one with the other one. So if we divide the first with the second, then we are going to have a 1 over alpha term. So in that case, we are going to have 1 over alpha and tangent in the left hand side. So if we want alpha instead of 1 over alpha, then we are going to divide the later with the former. So cosine minus sine, cosine over sine would be cotangent. Cotangent of alpha h tilde minus x. And of course, in our textbook, to avoid confusion, it also placed a bracket here. In the right hand side, similarly, if we divide this, then of course still we are going to have a minus square root of alpha squared minus beta squared. C prime will disappear, and what will remain would be cotangent of this value. Cotangent of hyperbolic cotangent when beta is well, once again, when beta is bigger than alpha, beta is bigger than alpha. So this would be equation 7.99 and 7.100. So what should we do with this, with these equations? Well, in this state, it will not be easy to how we can arrive at the final solution. So previously we defined we intentionally defined alpha and beta. Then if we substitute alpha and beta, then we will be able to get what how we solve this equation. So previously, by inserting alpha squared was defined. So in previously alpha squared was defined like this. This was the definition of alpha squared. And beta squared was defined. Beta squared was defined as this. So previously we defined alpha squared and beta squared in this way. And beta squared. So what does that mean? This equation should be, so let me simply So we know the first one, upper one, is the case when alpha is bigger than beta. The second one is for the case when beta is bigger than alpha. So if we insert alpha and beta, we should place a square root and this minus what would be br squared. br squared. So there is another thing that we need to enter, and br squared is given. So let's see where we can find that. BC and PR squared. That's so our textbook page equation 7.19. Here. So BR was defined as 2.40405 over R tilde. So if we utilize that, that's we always use PR squared. So 2.405 over R tilde and the square of this. So now we have what alpha is. This is alpha. And another thing that we need to utilize is the relation between H tilde and R tilde. And previously in the reactor is assumed that the diameter to height ratio equals 1. So it was assumed that diameter and height are same. So that means this R or R tilde will be half of H. So to reduce the unknowns, instead of R tilde, we are going to use H tilde, so half of H tilde. Divide by 2. So we just finished the left-hand side. And in the right-hand side, I'm sorry, once again, it should be beta squared minus alpha squared. Beta squared minus alpha squared. So in the right-hand side, beta squared, this would be alpha squared minus this would be beta squared. And alpha squared minus beta squared will be same. And one more thing. Then, so if we insert, so the right hand side here comes from the fact that we differentiate the neutron flux in the loaded volume and insert h tilde minus x instead of in the place of z. So if we place like this, then it is going to be once again plus, it is going to be simply x. So once again, this is going to be simply x. So to avoid confusion, we may insert the square root inside of the parenthesis. So what this affects is that square root of x, and in front of this we are going to have alpha squared, square root of alpha squared minus beta squared. In this case, so beta squared minus alpha squared, then the second term should be plus. Where this one should be that is correct. So instead of a cotangent hyperbolic, x in front of x, we have a square root of this. So in fact, so we need to solve this equation, the former one. So let's use the parenthesis, this parenthesis. So this is the equation. So the unknown that we have is in fact k. So this equation can be solved. We should use numerically for k. So if we calculate k, we are also able to calculate the reactivity. So in the left and right hand side, k, let's assume that k infinity is known. M squared only depends on the composition of the reactor. And h tilde is well, one thing that I missed is that instead of square alpha, we should place the square root of this part, which is alpha. So h tilde is already specified. It is related to the geometry of the reactor. So, and the reactivity words of the rod can be assumed that it is already known. So the only unknown in this equation is k. And we do not have any explicit form for k in this case. So previously also we utilized the numerical solution in calculating omega. So just like that, we should find k in a numerical way. So numerical solution should be found because we cannot have the explicit form for k. That means k equals something cannot be given in this equation. So at least what we know is that At least there are some limiting conditions. When all rows are out, when all rows are out, then let's find chi u here. Okay. So let's see our figure 7.9. So when all rows are out, in other words, when x equals 0, so in that case, that means the entire region is unloaded. The entire volume is unloaded. So this solution for unloaded volume will be applicable for the entire reactor. And in that case, the boundary condition, the condition for the upper boundary, that means C multiplied with alpha H tilde should become 0. And if we so in that case, so the solution should be identical to the case when we do not have a control banks. And then the alpha for unloaded case would be, so alpha for unloaded case, would be same with BH. Oh, I'm sorry, BZ. BZ. That is same with pi over H tilde. And that is given in our textbook. That is given in 7.17. So in our textbook, 7.17. So here we have BZ equals H over H tilde. So this should be same with the alpha for unloaded case. In other words, when all the control rows are out of the reactor. And when so in that case also K, the multiplication factor for this case can be not calculated. The multiplication can be found by simply comparing our parameters with the case of the with the with the solution that can be found in the previous sections of chapter 7. So the multiplication factor for this case was so k of unloaded case. So previously the multiplication factor was k infinity divided by k infinity divided by, or k infinity, let's write it as k infinity multiplied with probability of non-leakage probability. And this non-leakage probability was given in the case of when we apply two group, then 1 plus m squared m squared and br squared and bg squared. br squared and bg squared. So that can be found in equation 7.49. So our textbook 7.49. So 7.49, where non-leakage probability is given as 1 over 1 plus m squared and b squared. Of course, b squared equals br squared plus bg squared. So similarly, when control rows are fully inserted, so when all rows are fully inserted, of course, in that case, all area will be, all volume will be loaded, and this is chi rg for the entire region. And of course, when in that case the boundary condition would be when z equals 0, it should be also 0. And so in that case, we'd better utilize this equation. Here. So this would be the equation for loaded volume, and this chi r will be applicable to the entire region of the reactor. And in that case, alpha squared minus beta squared. In other words, this this would be the what is that? This would be the buckling for G direction. So in fact, this alpha squared minus beta squared should be alpha squared minus beta squared should be the buckling in G direction. So this will be same with BG squared and previously I told you that BG is defined here, defined as pi over h tilde. So because this is dg, it's a square should be provided. And the multiplication factor. Multiplication factor when all the control rows are loaded, all the control rows are fully inserted, then it is going to be 1 minus, because the worst row u, so this would be the reactivity worth of the control bank, and the multiplication factor will be reduced to this amount. So this is the case when all rows were unloaded, all the rows are out, and if all the control rows, if the control rows with reactivity worth low b will be inserted, then the multiplication factor after all rows are inserted, fully inserted, will be just like this. So what about when the load bank is partially inserted? In that case, of course, the situation would be somewhat more complicated. So let's see. First, our textbook. So the what we can see in figure 7.10 is the normalized control load bank worth versus insertion depths for the core of the heights. So this is the special case when control load bank, the reactivity worth of the control load bank is 0.02. So it is normalized with that. So 1 indicates the full strength of the control rods. So this is the case when control rods are not inserted at all. As we gradually insert the control load bank, So maybe this would be quarter of the reactor is now occupied by control load bank. And control load banks, this is the case when control load banks are inserted half of the reactor, and when the control load banks are fully inserted. And so in case this would be the case when, so you should instead of H tilt over L, this should be same with H tilt over M. So H tilt over M. So that means, what it means is that of course M indicate the migration length. The height of the reactor is about 10 times of the migration length of the reactor. And of course this M, migration length, will be determined by the composition of the reactor, like the absorption cross section and the diffusion coefficient, and also the property in the fast energy range. And the second one is that when the reactor size is much bigger than the first one, I also believe that this H is also a typo. It should be deleted here. So what we can see is that the trend is somewhat different in case of 10, in case that height is just 10 times of the migration length. So it is said that that is the case of loosely coupled core. Oh, I'm sorry. That is these smaller values of H tilt over M, like 10, is the case of neutronically tightly coupled core. So in this case, the reactor is tightly coupled, and the trend is very similar to the one that we have seen here. So this is the case of tightly coupled reactor core, and this is somewhat more larger reactor when the reactor is loosely coupled case. So of course loosely coupled case is the one with a large H tilt over M ratio, when the height of the reactor is 10 times of the migration length. So this word tightly coupled and loosely coupled from figure 7.11. So the first one is the case of a tightly coupled reactor core, and it shows us 3 different cases. So the first, when X is the depth of control load bank insertion. So when the control load banks inserted one quarter of the reactor height, half, and in fact 3/4 of the reactor height, and we can see that the shape of neutron flux will not significantly changed. That is, so this is the case. So that means neutronically the reactor is tightly coupled. So the upper part and the insertion of a control load in the upper part will also changes the shape, neutron flux shape in the lower part of the reactor. So that means if the neutron flux in the upper part is affected, then that directly also affects the lower part of the reactor. So the reactor is tightly coupled together. the second one is the case when the height is 50 times of the migration length of the reactor. So what happens is that this is the first one is the case when the first one is the case when the control load bank is inserted 1/4 of the height and half of the height of the reactor, and when the control load banks are inserted 3/4 of the reactor. And what we can see is that in this case neutron flux is affected. Neutron flux that control load banks are inserted are greatly affected, while so if this is the upper part of the reactor and this would be the lower part of the reactor, control loads will be inserted from top to the bottom. So as control loads are inserted, then we can see the shape of the neutron flux changes. But what we can see is that as control loads banks are inserted, the neutron flux decreases. So in the upper part, the neutron flux will be affected, while this lower part will not be significantly affected. On the other hand, the shape of neutron flux in this area actually increases. So this is the case when the case of loosely coupled reactor core. So I also would like to show you that so we are able to also develop. So previously I told you that we need to numerically solve this equation. So after solving this equation, numerically solve this equation, and if we calculate the shape of neutron flux, then for tightly coupled reactor, when the height is about 10 times of migration length, and so these graphs were used to find the solution for K. More specifically, the ratio of K infinity over K. And it is like we found the solution here. So K infinity is 1.33 times of multiplication factor. And if we use this, then this blue part will be chi u. In other words, this blue part will be the neutron flux of unloaded volume, and this orange part will indicate the loaded part. So if we gradually increase, we insert the control load of about 40%, then still you can see that still this shape is maintained. If we insert like 80%, then this will be unloaded part, and this would be the loaded part. So the shape of neutron flux does not significantly change as we insert the control load bank more and more. However, in case of loosely coupled reactor core, so when we insert the control load bank about 20% of the height, so this orange part indicates the control, the flux of the neutron flux when the control loads are inserted, and this blue part will be the control load neutron flux in the unloaded volume. If we insert the control load more from 20% to 40%, so now you can see the neutron flux is changed, and if it becomes 60%, oh, I'm sorry, I entered the wrong number. So it is changed, now changed to like this. If we insert 70%, so it gradually changes like this. So all these graphs could be produced by numerically solving k in this equation, and after that, then if we solve the equation, then the k, like, where is that? So this k will determine alpha. So k will determine alpha squared and also beta squared. And by determining alpha and beta, we will be able to calculate neutron flux, the shape of neutron flux in unloaded and loaded volume. So this would be your another challenge problem that is given to you. If anyone is able to solve and find the graph that I just showed you, or the graphs shown in figure 7.10 and 7.11, then just solve this problem and then just let me know. So this would be end of today's lecture. We just finished also section 7.6 today, and next time we are going to move on to chapter 8, which is about energy transport. So see you next Monday.